do a little bit of review here. One of the things we discussed in Chapter 4 was Pascal's triangle. Do you remember how Pascal's triangle starts out? 1 and a 1. How do I get new levels in Pascal's triangle? You put 1s on the outside, and to get these inside numbers, you add. Oh, yeah. Yeah, it's been a minute. It's been a minute. Try and fill in the next level. Or if you get that, fill in the next level after that. How about level 4? Amadou, what's that going to look like? What number is going to go here and here?
4.
Well, what's 1 and 2?
Oh, 3.
And then 3 again. Let's put a couple more numbers out here. 1 and 1. And do the same thing again. McKenna. I always lose track of you because you're like right behind my projector here. What numbers should I put this next level?
So it's going to be the 3 and the 1. Is that what I'm adding?
Yeah.
So 4.
4.
And another 4.
3 and 3 is...
6.
And then the other 4. All right, somebody be bold. Somebody be brave. Who's got that 5th one? Bryn, hand up pretty fast on that one.
All right, 5, 10, 10.
Nice. Now there's an amazing amount of cool patterns here. Down this row you have your counting numbers. Down this row you have what are called your triangular numbers. So what are triangular numbers? Well, triangular numbers are kind of just what they sound to be. They're these numbers that you would add up like the number of pins in a bowling alley, right? 10 pins when you first roll down the alley, or the next one would be 15. So those are your triangular numbers. The next row over to that, the 1 and the 4 and the 10, etc., those are your tetrahedral numbers. So what's a tetrahedral number? That's kind of weird. It's kind of like bumping up your triangular numbers one dimension. So it's how many would be stacked in a pyramid. So 1, 4, 20. And then the next one would probably be 35, I'm thinking. But I'm not sure. I'd have to think about that a little bit more. Yeah, actually it would be 35. So tetrahedral numbers. There's some stuff called Fibonacci numbers that I won't bother you with. The numbers across these rows are all powers of 2. So that's kind of pretty wild. And by the way, this is called Pascal's triangle, but Pascal didn't invent it himself. Here's Pascal's triangle in Chinese circa 1303. Here it is in Japanese, Hebrew. Now I have looked for it in Arabic, but I haven't seen it exactly the way that I could relate to it yet. So if someone wants to help me out with that, that's great. There's one other little pattern. Oh, here's just kind of an amazing thing. That if you take any number, like take 15, and then when we take a look at the numbers around it, 6 times 10 times 35 is going to equal 5 times 21 times 20. Just bizarre. I mean, they could spend literally an entire class talking about properties of Pascal's triangle, but that goes beyond us. Hopefully you picked up a couple that were interesting to you. You know, triangular numbers, tetrahedral numbers, or that multiplication pattern. That's kind of cool. Pythagorean theorem. We spent some time with that. That's one thing that most people remember years after they've gone through their math class is a squared plus b squared equals c squared. That applies to what kind of a figure? Right triangles, A, B, and C. This is your 90-degree angle. That's where you get this. You should be able to solve things for the missing side if you're given a right triangle. So in this particular case, if I had A was 12 and C was 15, that would be 12 squared plus B squared equals 15 squared. So that's 144 plus b squared equals 225. Is that right? Yeah, 225, yeah. If I subtract, I get b squared equals 81. If b squared equals 81, what does b equal? 9. And put in the right units there for me. That'd be 9 inches. Assuming that I started out with inches, or whatever the right units would be, meters, feet, miles, parsecs, astronomical units, whatever you want to use. Make sure that they're the right units. Now, one thing that you can get out of the Pythagorean theorem is a distance formula, distance between 2 points. So distance between, say, x1 and y1 and x2 and y2. So that distance is really coming from subtracting the x's and finding a horizontal distance. So that'd be x2 minus x1. And then finding the vertical distance, y2 minus y1. Those both get squared and summed. I'm not sure why, but a lot of times when I see people doing this problem, they write the formula with a minus here. That could lead to the square root of a negative number, which for this class is really bad. We're not going to deal with the square root of negative numbers. So, yeah, it gives you imaginary numbers. They're pretty cool. In fact, here's some Thanksgiving humor for you. If you remember what this is, square root of negative 1 is I. All right, that's the imaginary number. I could talk a lot about the history, but the Thanksgiving joke is this. What did you do on Thanksgiving? I over 8. Oh, come on, give me some love. I had to wait a whole semester for that one, man. Oh, good deal, good deal. All right, so there's, I know, I'll keep my day job, right? Can you use the distance formula to find the distance between 2 points? You got some nods on that one? All right. So points something like -2, 3, and 2, and let's see, 2 before 2 and 6. You should be able to find the distance between those 2 points. I think if I did this right, it should be 5, but I'll let you play with that. We dealt with the margin of error. So you see this in terms, in like election cycles, that people come out with polls. We talked about a poll for us in this class. That was the poll of the race for mayor in New York City. And here we go. So we had, I still don't know how to pronounce it. Sliwa? I'm not sure.
Call it
S,
S.
yeah, we'll call it S. So S, Cuomo, and Mondami. This was the polling numbers before the election. Go ahead. Mondami?
No, I'm done.
Mondani? Do I get the N and the M reversed?
No, I wasn't laughing at you. I made a funny joke.
Oh, okay.
Not,
Do you want?
no.
Yeah. All right.
No, not sure what class.
I'll tell you why later when I'm not recording. But yeah, I have this PTSD of somebody laughing out of turn. I'll share with you why, but not while I'm recording. In any case, so this was the estimate of where they were standing before the election. S was somewhere around 16%. Cuomo was around 32%. And Mondami was around 48%. Those were the pre-poll numbers. But the thing is, if you take a different poll, you're going to get different people to answer. You're going to get a different mix. So it's not enough just to have an estimate of where you think you're at, just 1 point. You want to surround it by a confidence interval, a margin for error. You're like, well, we know it's not going to be perfect, so let's do this. And you put in that margin of error. Now you're saying, well, this is our estimate, but it could be as high as this or as low as this. So that's the width of these intervals. So from say around 27 to around 36. Okay, so somewhere in here is where we think that Cuomo is going to be. That's what that margin of error is. In fact, let's look at some polling numbers. Trying to think of something. Well, unfortunately, I'm not trying to get political. Let's do Trump approval rating. Now, it should give us some plus or minus numbers as well. Let's see here. Of course, I got to sign in for something. Forget that. Right now, I want to see the plus and minus numbers. They're not telling us the margin for error. All right, usually they do. Let's try one last one, which is polling report. I'm not sure they're updating this much anymore. I guess not. All right. But if we had, let's say, 62% are in favor of proposal A, plus or minus 3%. That 3% is your error. And what that means is it could be as high as 65% or as low as 59%. Add 3 and subtract 3. So this is your margin of error. Now, we don't know where the actual true value is, but we think it's someplace in there. And that's the interpretation of that plus or minus stuff. Now, sometimes, your margin of error might be too big. You might say, well, that feels pretty wide, 59% to 65%. That feels too big. So if you wanted to decrease this, you're going to need a larger sample size. And that's what you'd use this calculation for, is to figure out, well, how big your sample size should be to make this term even smaller. What I want you to know is I want you to understand that, whatever this is, it's your estimate, and you're giving yourself some margin for error. You should be able to go from, say, this to this. So if I gave you, a proposal, or excuse me, some polling numbers for proposal B, maybe it's less popular, maybe it's 48% plus or minus 4%. What would that be? What would the interval be if this was your polling numbers for some issue? 44 to what? 52. And finally, I guess I could do it a different way. I could give you the numbers like this, 50 to 56, and ask you to write it like this. So now how would you write it? What would it be? Something plus or minus something. Some number plus or minus your error. What would that number be? What would the error be? So your number here is going to be what's in the middle. So it's going to be 53%. Now how far above and below are these numbers? 3%. So there's a couple ways I can ask you to do that. I'm making an executive decision right now. I'm not going to ask you to use this number, or not ask you to do this one. It's nice. It's not too hard if you did try and play with it. And I would give you this formula. I'm not going to make you memorize that formula. But maybe that'll be an extra credit type question here. Okay. In section 4.4, we dealt with direct and indirect variation. So, direct variation, indirect variation. Which one is which down here? So this one would be direct, and this one would be indirect. How can you tell if something varies directly? What's the acid test for it? What's that? It goes through the origin. Good. Another thing is if you double the input, what happens to the output?
Doubles.
Double the input, double the output. Good. So double the input doubles the output. Now what happens if you have indirect variation? What if you double the input there? Yeah, it's going to halve the output. It's going to, so doubling the input cuts down the output by half. So halves the output. Now I'm actually going to use this for a couple different things. This could also represent exponential decay. Yeah, I guess it would actually touch the x-axis, so maybe it's better for indirect variation. But exponential decay is one of those things that we did see. It's kind of the opposite of exponential growth. When you had, where is it? Let's go to this one. Let me shut these off. When we had our interest rates, maybe we had, 5 times 1.04 raised to the x power. That was an example of exponential growth. There you go. There's their exponential growth. You could also have something that decays exponentially. So y equals 5 times, say, 0.96 raised to the x. So there you go. They're kind of a mirror image. One is increasing, one's decreasing. But at the same time, both of them are exponential functions. Just one's increasing, one's decreasing. Now the amount of blood in your, or caffeine in your blood after drinking a cup of coffee, is that going to be an example, do you think, of exponential growth or exponential decay? Yeah, decay. Because after a while, your liver and your kidneys are going to kick in and filter all that stuff out. So yeah, after a while, it's going to decay, and it tends to decay exponentially. Let's flip over to the back side. And in my haste to get this together for you guys, I did the same thing twice, so bummer. But this will give us a way to, we'll make do out of this. So population of a ski town appears like this over time. And you're asked to find the growth or decay rate. How are you going to do that? How are we going to find the growth rate or decay rate? One thing you could do would be look at this compared to this. The new one compared to the old one. So for instance, R in this case would be 9,000 divided by 10,000, which gives you 0.9. We can look at the growth and decay rate for this next one. Try that one. What two numbers would I put together for that one, Brittany? Find the growth or decay rate between years 1 and 2. 8,100 divided by 9,000, and, well, we get 0.9 again. Emma, I need another one. I'm assuming you're right as well. Nice. So there's how you can find your growth and decay rate. But let's do a couple other things here. What if I wanted to find this next term here? What could I write here that would tell me what that next term is? So if this was in Google Sheets, and I'm assuming that, let's see, this would be column A and B, 1, 2, 3, 4, 5, 6, what I could do is I could say, all right, well, that's going to be B6 times 0.9. And then I could copy and drag that cell, that formula, all the way down. So that'd be one way to do this. There is actually another way to do this, and we'll talk about that in a second. I'll let you copy this as well. You could actually work with the original population, and this is going to be 10,000. I'm just showing you the pattern here. This is going to be 10,000 times 0.9. And then I'm going to take, to get from here to here, I'm going to multiply by 0.9 again, which gives me 10,000 times 0.9 squared. And this is going to be 10,000 times 0.9 times 0.9 times 0.9 again. Or instead of writing 0.9 times 0.9 times 0.9, I could write 10,000 times 9.9 to the third power. Any suggestions as to what this one's going to be down here? Yeah, to the fourth power. So what I could write in general if I wanted to, you know, at some nth level, yeah, 10,000 times 0.9 to the power of whatever cell this is, raised to the, you know, the nth power, which is going to be a sub whatever, the a nth cell. But yeah, you can write this in general. You can write a nice general formula for this. Now, it helped out that I put a 0 here. Otherwise, this formula would have a -1 in the exponent. That's okay. So there's a couple different ways you can come up with a general formula to help populate these cells. And that would be, you know, something that you could use here. All right, let's kind of follow that up a little bit. One of the things that we could do here is take a look at our golf ball data. And it's not going to work out perfect. That's okay. What's going to be the rate of decay here? And I'm using decay because you can see that this curve is decreasing. Well, that one we're going to have to take out a calculator. Let's round it off to the nearest second digit. Skylar, what numbers should I divide here to find the rate of decay for the first bounce?
You divide 29.7 by 80.
Good, thank you. 29.7 divided by 80, so about 0.37. All right, so that's good, 0.37. Let's do the next one down. Let's see if we get about the same thing on the next one down. So for the next one down, Taya, what else should I divide?
The 29. Are you doing the 10.7 by the 29? Or are you
Yeah,
doing that
10.7 divided by 29.7. Sure. So 10.7 divided by 29.7, about 0.36. Okay. No one said these were perfect. We can do one last one. We can do 3.7 divided by 10.7. And we're still in that same kind of ballpark there, about 0.35. It's hard to do these things exactly. I think you guys had outstanding results just based on this. Yeah, it's slowing down a little bit, it seems like, so we're losing more energy. But what it turned out to be is that 0.37-ish, that's the percentage of height that the ball returned to. So whatever height it was, it returned to 37% of that height, and then 37% of that height, and then 37% of that height, and eventually it just got too small to measure. Some of you guys had some outstanding measurements. Good job on you. What did the 80 tell us in our model? Our exponential model was this. It was y equals 80 times 0.37 to the x. What's the 80 tell us?
Starting dropping.
Yeah, the starting height. And the 0.37, that's the proportion of height that the ball returned to. The proportion of height the ball returns to. So you're getting about 37% is high on subsequent bounces. Somebody, and I forget who, and I'm sure I gave you extra credit, had a good idea that maybe I should bring in different balls. Maybe I should bring in a tennis ball, a basketball, golf balls. I'll probably do mostly golf balls. I don't think I want a lot of basketballs in the hallway. I'm sure I'd probably run afoul of somebody, but no, that was a good idea, and I think I'll do that next time. I like that experiment. And looking at your work, I think you guys did too, so that was a good thing. Yeah, some other things. Certainly my dogs have enough balls running around the house. Could round up a few of those pretty easily.
My family's a softball and baseball family, so we have like ball bags.
Ball bags. All right. Softball would be pretty good. Maybe you're nervous having hard balls around here. Okay, let's keep going. Perimeter of a yard being enclosed by 120 feet of fencing. So your perimeter, assuming it's a rectangular shaped yard, is going to look like this. You're going to have a length here, a length here, and a width here, and a width here. So your formula for the perimeter is just 2 times W plus 2 times L. That's right here. And you've got 160 feet of fence to work with. Or excuse me, 120 feet of fence to work with. So that gives you this. 120 is 2L plus 2W. If you divide this relation by 2, we can get rid of the 2's. That gives you 60 equals L plus W. And what I'm going to do is I'm going to replace W in this formula. And replace W by 60 minus L. So now the area of my enclosure just is going to depend on this one variable, L. So we're going to see what happens when we change the value of L. Now I know I'm running up against time. If you have to go, you have to go, I understand. But let's take a look at what happens to this when we graph this. And we have to fill out a table first. So keep in mind that the width is 60 minus the length. I did take attendance, thank you. Although some people came in late, so if you came in late, I have to hopefully remember. 60 minus L would be 60 minus 0 would be 60, 50, 40, 30, 20, 10, and 0. Since the area is length times width, we can figure out these areas. It'd be 0, 500, 800, 900, 800 again, 500, and 0. If you graph that, let's put in some plots here, some points here. 0 here, 0 here, 30 and 900. Let's fill in a few points in between. At 10 we had 500, at 50 we had 500, and at 20 we had 800. What's the shape of this graph? A parabola. According to this graph, what value of your independent variable maximizes the dependent variable? Where's the maximum?
900 at 30.
Yes. Now there is one thing that I'm going to ask of you guys, and that is when you're graphing something that you label your graph. For instance, in this graph on the x-axis I've got the length. What should I label my y-axis with? What's the area? So the length is actually in feet. The area is in square feet. So according to this graph, the value of the independent variable that maximizes the dependent variable is 30 feet. And at 30 feet, you're going to have 900 square feet of width. In fact, can anyone tell me the shape of my rectangle if I use these dimensions? Yeah, it's going to be a square. So the units for column H and I would be feet and square feet. I guess I'll just kind of remark quickly on this one. How do you find your profit function? Profit is revenue minus cost. P equals R minus C. When you subtract those, you're going to get a polynomial, and you can use that to find the graph of your function, and then find the maximum and minimum from there. Section 4.9 was some factoring. We did our factoring practice earlier. So practice factoring and the quadratic formula. Know that, be able to write it, and we'll all be happy. Whew. Oh, one last thing. This review sheet is hot off the press. It took me a while to put this together. So I would strongly suggest you look at this carefully for your exam. All right? If you have some questions, come catch me during office hours.